before I forget. Last week of classes, I don't know how you would have missed that. It's very exciting. Even for me, I'll miss you guys, but it's nice. My plan for today, we're going to finish chapter 8, sections 4 and 5, and then that'll be the end of new material. And then what I want to do for Wednesday is give you a final exam overview, just an idea of kind of where the grades will be distributed and what kind of questions to expect. Okay. And then I'll post some chapter 8 practice problems that we'll go through. I did not finish them before class. Otherwise, I wanted to post them before class, but I did not. So that was bad. But I shouldn't have said anything. Now you know that I did bad. But I suspect that we'll have some time to work on the problems and then go through the problems. And so we'll kind of, because everything else you'll have seen on the final exam and you'll have done the practice test for. And so I just want to do a little bit more practice for chapter 8 overall. All right. And then that's it. Crazy. Any questions about that before we start? The beginning of the end. Yikes. So we've been working on probability, and we've been working we haven't called it conditional probability, but we have seen conditional probabilities already. Okay. And so conditional probability is when or when a previous outcome, let's say it like that, when a previous outcome affects the probability of another outcome. For example, when we were drawing marbles, right? We had red marbles, white marbles, blue marbles, whatever. If we're drawing without replacement, right, then the probability of drawing a red marble, well, it depends on if you've already drawn a red marble, right? And so as a quick example, consider drawing marbles without replacement. Oops, replacement. Right, knowing that you drew a red marble first, that will affect the probability of another red marble. Right? You can also call this conditional probability is what we call them, but it might be helpful to think of them as dependent probabilities. Right? The probabilities depend on another outcome, right? Or another probability. So if a family has 3 children, find the conditional probability of having 2 boys and a girl, given that the firstborn is a boy. Okay? And this given is a word that you're going to want to keep an eye out for. Okay? And so that's what indicates that this is going to be a conditional probability. There's some notation that I'm trying to hold off on introducing for a little bit longer, we introduce it here in this green box. So we're not that far away, but I just want to introduce the concept of the conditional probability first. So what we want to do is we want the probability of having two boys and a girl, knowing that the firstborn is a boy. And so if we have three kids, then I think that the easiest way to map out all the possible combinations is a tree diagram. A tree diagram. I know, I'm so predictable. So here we have child number 1 is either a boy or a girl. Child number 2 is, oops, that doesn't look like a B. A boy or a girl, boy or a girl. And then for 3, boy, girl, boy, girl. Boy, girl, boy, girl. Child number 3. At the bottom, I like to write out all the probability or all the combinations that I have, right? And so boy, boy, boy. And what you want to do is you want to consistently run down each set of branches so that you write them out in the same order, because order matters. Boy, boy, girl. Boy, girl, boy. Boy, girl, girl. Girl, boy, boy. Boy, oh boy. Girl, boy, girl. Girl, girl, boy. Girl, girl, girl. Ah. Okay. Now, from last week, we know we could assign probabilities here, but we don't need the probabilities explicitly, so we're okay.
Could we not have done like the 3? Oh wait, never mind. That's another question. Never mind.
All good?
That's
Nice. No, because they happen consecutively, right? Then you have to list them in that.
yeah, and I was gonna say to put like a third one at the child 1, but that wouldn't make any sense.
Oh,
A boy, yeah.
we assume only 2 genders because it makes our tree a lot easier too. So, how do we kind of tackle this now? We want the probability of having 2 boys and a girl. Let's figure out where that happens first. So 2 boys and a girl. I'm going to circle them in green wherever that has happened. All right. 2 boys and a girl. 2 boys and a girl. That's 1 boy, 2 girls. 1 girl, 2 boys. And that's it. All right. Now, in general, we could find the probability of 2 boys and a girl is 1, 2, 3 out of 1, 2, 3, 4, 5, 6, 7, 8. Right? And so we don't need to, but just for extra practice, right? The probability of 2 boys, 1 girl is 3/8. And then the firstborn is a boy. That's the conditional or the given information. And so what that means is we're told that, hey, just so you know, the firstborn is a boy. Which means that the firstborn has to be a boy. You're forced down this branch. Right? And so really what you're choosing from then, instead of all 8, now you're restricted to all the branches that came off of the firstborn being a boy. So if you wanted to, we could talk about the probability that the firstborn is a boy, that would be all of these 4 out of 8, right? Which of course maps back to 0.5 or 50% because that is what we're assuming the probabilities are anyways, right? And so 4 over 8. We want to find, oops. The probability of 2 boys and a girl given that the firstborn is a boy. And so now I'm restricted to this as being my sample space, right? I only have 4 things and 2 outcomes satisfy the criteria. So we want the probability of 2 boys and 1 girl given firstborn is a boy is 2 divided by 4. Or 1. If you want. Nice. Any questions about that one? All right. 1 6-sided die is rolled once. Find the probability that the result is even. A good place to start, if you just have, well, a good place to start in general is to list the sample space, right? And so the sample space here would be 1, 2, 3, 4, whoops, can't write anymore, 4, 5, 6. The probability that the result is even is the number of outcomes that are even out of the total, right? The total, I have 6 possible outcomes, and 2, 4, or 6 is the probability of 2, 4, or 6, which is 3 over 6. I don't usually reduce the fractions. It's not really worth the time, right? But if you want to write it as a decimal, that's totally fine too. Then find the probability that the result is even given that the result is greater than 3. So now we know that the result is greater than 3, and now I want to know, okay, well, what's the probability that it's even then? And so here I'll clarify greater than 3, not including 3. It doesn't, I think that's hard, right? If it was including 3, it would say at least 3, right? But greater than 3 does not include 3. On the final exam, I'll be clear, right? Including, and then I'll put in brackets, not including 3, just so that you don't have to second guess yourself. Okay, find the probability that the result is even, given that the result is greater than 3, which means that, okay, the even ones I have to choose from are 2, 4, or 6, but the result is greater than 3, not including 3, is 4, 5, or 6. And so I know that the result was either a 4, a 5, or a 6. So the probability that it's even, given greater than 3, is 2 out of 3. 4, or 6 out of 4, 5, or 6. Which is only 3 outcomes. Oh. Nice. How about the next one? Unless there are questions. I trust you'll stop me, but I also feel like I need to ask every now and then. A fair coin is tossed twice. Find the probability that the result is 2 heads. No, probably just one. Is 2 heads. Huh? Again, it might be nice to have a look at the sample space, right? And so you toss a coin, heads or tails, and you toss it again, and you get heads or tails, heads, tails. So then you can get heads, 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 tails, tails, heads, tail, tail. Which you had to do on test 2, right? List all the possible outcomes. Right? And so if we want to find the probability that the result is 2 heads, well, that's the probability of H. Right? There's only one thing out of the 4 that makes that happen. What if we have to find the probability that the result is 2 heads, right? Given that at least 1 head is obtained. Now you're restricted, right? You know that it has to be one of these 3, and HH is one of those 3 possible outcomes. And so here, given that at least 1 head is obtained, puts me out of 3 instead of out of 4, right? It adjusts the probability. So the probability of head given at least 1 head is 1 out of 3 instead of 1 out of 4. And I guess in both scenarios, 2 heads, 2 heads. Nice. Introduce a formula for what we've been doing, but also a little bit of new notation that we'll talk about. Is, and let me maybe, just maybe, bump these down, because I can tell I'll need more space anyways. Hey, the heck. Okay, maybe not. Doesn't want to do it. Fine, I'll do it the other way. Add a page here. And bump this up to the top. Hopefully it behaves. Phew. And let me crop this up so I can make it bigger. So if we have 2 generic events, E and F, then the probability of E given F, which is what we've been solving, right, is first off written like this. So the given is denoted by this vertical bar. And so you read this as the probability of E given F. And so the probability of E given F, you read it as the probability of E given F. Okay, so that vertical bar, you read it as given. What this probability is going to translate to, though, is something that we are familiar with. The probability of E and F, right, over the probability of F. And so notice that it's the probability of E and F divided by the probability of F. And so if you kind of notice the pattern, you don't need what's on your formula sheet, although it is on your formula sheet. But I do want to also make a note here, because it comes up sometimes. Note, the probability of E and F is the same as the probability of F and E. Since the order that we multiply in doesn't matter, right? And means multiplication in some way, right? And so the order doesn't matter. The order around and doesn't matter. So even if you're working on a problem and you find that you need the probability of E given F, but maybe you only have the probability of F and E, which is not exactly what you want here, just remember that that's the same as the probability of E and F. Good. And so, of course, it's on your formula sheet. We'll come back to the multiplication rule. We're doing the conditional probability now. And so here's what's on your formula sheet. And it looks exactly the same. On your formula sheet. Nice. So the key word that you want to be looking out for is this given, right? Or knowing that blah, 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 right? Given this, what's the probability of another thing? Oh, nice. So now we're going to solve this problem, find the probability that the result is even given that the result is greater than 3, right? But using the formula instead. So we already know the answer. A single die is rolled. Use the above formula to find the conditional probability of obtaining an even number given that a number greater than 3 has shown. And so what we want to do is, let's call this an even number. And for simplicity, how about a number greater than 3 can be F. Because that's the given information. And so even though F doesn't really make sense, right? But it is the given information. So in terms of our formula, this will be the nicest way to map it out. We'll outgrow that and we'll be able to map from different variable names, but it's our first time. So we want the probability of E given F. Which means from the formula sheet, I guess, we want the probability of E and F divided by the probability of F. Oh, I should use the oops, the intersection symbol to match the formula sheet. But you read it as and, right? Okay. What that means is we need to find the probability of E and F. Now, E and F in words, E and F is an even number and greater than 3, not including 3. So if we have our sample space, I'll toss it up here, 1, 2, 3, 4, 5, 6. The probability of being even and greater than 3 is 4 and 6, but out of the total 6, right? And so the probability of E and F is 2 out of 6. And then the probability of F, the probability that the number is greater than 3 is, not including 3, would be 4, 5, or 6. So 3 out of 6.
For the first one, the probability of E and F,
Mm-hmm.
I thought it had to be even and greater than 3, which would then be 2 out of 3, because you would only look at 4, 5, 6. Right?
So you want to be careful because that would be given that it's greater than 3. So knowing that it's greater than 3, but when it's and, it's out of the total.
Okay.
Yeah. Mm-hmm. You can put it in into your calculator. As long as you use brackets, it should just simplify for you, right? You can try it on your calculator, get to know your calculator. 2 over 6 divided by 3 over 6 puts me at, well, I guess if your calculator doesn't give exact answers, or 2 over 6 times. A refresher on dividing fractions might be nice. 2 over 6, right, is a fraction over a fraction. If you've got a fraction in the denominator, then you flip it and then you multiply it. So times 6 over 3. Or really, if they're over the same thing, they'll cancel. Right? They just go away, but it's because of this. And so the answer is 2 over 3. Which of course is the same answer that we found. But what's nice about having a formula is that you don't have to be able to draw out your sample space, right, to count out how many scenarios satisfy the outcome. Well, any questions about that one? I'm surprised we haven't seen more of these. A really common way of delivering probabilities and asking probability questions is through a table, right? A table of counts. I think there's been some in the homework, right, where you've had to read some tables, but maybe you haven't done it yet because I think the first one is due tonight. I think. So we can start. We'll find those probabilities eventually. But for practice, oh, I wrote that weird. For practice, find the probability of M. So the following table shows the distribution by gender of students at a community college who take public transportation and the ones who drive to school. And so we've got the gender here. Gender is in the row or in the columns. And then how they get to, oops, not all the way. How they get to school, presumably, is, let's call it the transportation, is in the rows. How you read this is that there were 8 students who took public transportation and are male. There were 13 students who took public transportation and are female. Right? And then finally, 21 out of 100 took public transportation regardless of their gender. And then do the same thing for the driving. But for the males, right, 47 out of 100 were male and 53 out of 100 were female. And so for practice, the probability of someone being male in this group would be 47 out of 100. What if we want to find the probability of F and D? So female, and they drove to school. That's this overlapping region, right, of 40. And so we have a count of 40 out of 100. Just as a note, this would be T and M. Oops. But of course, it could be M and T if that's what you need, right? Because around the and, it doesn't matter. This would be T and F. This is D and M. And this is D and F. And out of the 100, right, gives you the overall probabilities. So now, what if I want to find oops, I'll use regular color here, the probability of D given M. So the probability that they drive given that they are male. And so if you use your formula sheet, on your formula sheet, you have this generic E and F, and maybe I'll bump this down here. Oops. So what you want to do is you want to map your D to wherever you see an E and your M to wherever you see an F. And so this is going to be the probability of D and M divided by the probability of M. Right? I actually find that it's harder to kind of map back and forth between the formulas. I think it's a good place to start. But once you see the pattern, right, that it's the first one and the second one divided by the second one, right, down here, then I think that that's a little bit easier in the end, right? But you have the formula in case you find that it's helpful. So from the table, I need to find the probability of D and M, as well as the probability of M. The probability of D and M, right, so they have to drive and be male, is 39 out of the total 100. So 39 out of 100. Then divided by the probability of males. Now the probability of males, right, we found earlier, but let's do it again just for practice. The probability of a male, regardless of how they got to school, is 47 out of 100. So I get 47 out of 100. Now you could use your calculator and you could find 0.39 over 0.47. That's totally fine. But because you're dividing by the same number, you could just cancel them out if you want to. They have to be the same, though, for you to be able to do that. And so the probability would be 39 out of 47. Another way that you could do it, since you have the table, is you could say, okay, well, the probability that they drive, knowing that they're male, right, that restricts my total to be out of 47, right? And so how many of those 47 drive? 39 of them. So 39 out of 47. That would be fine as well. But it's nice. I want you to try to use the formula. But you can just use the table as well. How about the probability of F given D? So the probability that they're female, given that they drive. How about this time we practice using the table? So now I know that they drive, right? So I'm restricted to this 79 total. And then how many of those drivers are female? 40 out of 79. So equals 40 out of 79 from the table. Or using the formula sheet, the probability of F given D is the probability of F and D divided by the probability of D. Probability of F and D is 40 out of 100. Right? Don't let that trip you up. Trips me up sometimes. Let me bump these down. So it's 40 out of 100. And then the probability that they drive, that's all these guys, so 79 out of 100. Again, the cheater way, cancel those over 100 over 100. It's really cheating. It's okay cheating though, because you're just canceling multiples. Anyways. But we don't have any time left in this course to practice more fractions, so I gotta give you the cheater way. You can use your calculator too. And you're allowed to give decimal approximations, right? 40 out of 79. 0.506329, blah, 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 blah. That's fine. Nice. So we found the same answer. Just depends on how your brain works, right? If you're having a hard time looking at this table and figuring out what's been given and then restricting your total to that information, then the alternative is to use the formula. Just figure out what is easier for you. Okay. Either solution is accepted on the final. All right, so figure out which one you like. Just use that one. All right. I like the formula, which usually means you guys like the table. But the formula is always a sure thing. You could try both. The probability of M given T. Oops. Is the probability of M and T divided by the probability of T. Try to wean you off of the table. But you're allowed to use it, so I shouldn't do that. M and T. Male and public transportation is 8 out of 100. Over the probability of T, which is this overall 21 out of 100. Which puts me at 8 over 21, which would, of course, let's see, be the same answer that you would get just using the table. So we know they take transportation, public transportation. All right, so we're restricted to this 21 now. And how many are male? 8 out of 21. Good. Any questions about those ones? What if you're given probabilities? The probability of E is 0.5, the probability of F is 0.7, and the probability of E and F is 0.3. Huh? Yeah. I know. I don't know why they do that. Sometimes they go like kind of hard and then they throw in an easy one. It's weird. Just remember, the only thing that might trip us up here is that this is the same as the probability of F and E, right? Is 0.3 or 0.3. Just because I can tell that we're going to need that. But yeah, knowing this information, we don't have to do any work. Well, some work, but not compared to what we were doing. The probability of E given F, mapping it out from our formula, is the probability of E and F divided by the probability of F. Now I have both of those components, so it's really just a matter of plug and chug here. 0.3 divided by 0.7. Does it make anything nice? Not really, just 3 over 7. I'll do a decimal. How about 0.42857, 14286. Versus the probability of F given E. If you read it, right, it would be the probability of F and E divided by the probability of E. And that's where you might get stumped just briefly because I don't have the probability of F and E, but you do because they're interchangeable inside. All right. And so here, the probability of F and E, and E over the probability of E. And this is the one that E and F is the same as F and E. Which means we have 0.3 over the probability of E, which is 0.5. 3 divided by 0.5 puts me at a beautiful 0.6. That's always exciting. Maybe only exciting for me.
No, I like that.
Yeah, when it works out nicely. Mhm. E and F are mutually exclusive events. Uh-oh, drawing from last week. Mutually exclusive means what? So then the probability of E and F must be 0. The outcomes is the empty set. The probability is 0. I know. Gets tricky. But you got it. You got it. If E and F are mutually exclusive, by definition, I'll write out what we were talking about here just so we can see it. By definition, E and F is the empty set, right? No overlap. Which means that the probability of E and F is 0. Right? They can never happen at the same time. Will never happen together. That distinction takes a long time. Right? But so really what we're told is that the probability of E and F, as well as the probability of F and E, if that's what we need, is 0. Right? That's what we're being told by being told it's mutually exclusive. Probability of E is 0.4, the probability of F is 0.9, and we want to find the probability of E given F. Probability of E given F is the probability of E and F divided by the probability of F. Now, if they're mutually exclusive, which they are, that would be 0 divided by 0.9, which puts me at a beautiful 0. Easy. Easy 0. The one thing you always want to remember too, because this one is a little bit tricky, I think, is that probabilities have to be between 0 and 1. Oh, any questions about that one? Because it is a little bit sneaky. If we have the probability of F given E is 0.5, and the probability of E and F is 0.3, and we want to find the probability of E, okay, then I have the probability of F given E is the probability of F and E divided by the probability of E. Again, E and F, these are the same. Right? Inside, they're interchangeable. So if I want to find the probability of E, but I have 2 out of the 3 things still. They're just a different 2 out of 3. And so what I want to do is I want to plug in the values that I do have. The probability of F given E is 0.5. Is the probability of E and F, which is the same as the probability of F and E, so that's 0.3 divided by the probability of E. Bump this down. Solving for the probability of E, what are you going to have to do? You'd want to be careful because then the P of E would be in the bottom still. So you want to send it up top first, which puts you at 0.5 times the probability of E is 0.3. And then what you want to do is you want to send this 0.5 over here to shake out the probability of E where it is on the level that you want it to be. And so that puts you at the probability of E is 0.3 divided by 0.5. Which is that same beautiful 0.6. What's nice here is if you had to do this, you could check your work, right? You could plug in 0.6 because you know 0.3 divided by 0.6 has to be 0.5. If it doesn't, you did something wrong, right? And so you can always kind of go back and check your work, which is nice. Nice. Good. Let me just check the formula sheet because it's on here. Here, right? If we just in general rearranged, the probability of E and F is the probability of F given E times the probability of E. Right? And so it's sort of on there. Right? What did we do? We multiplied this P of E over, so this P of E went over here. And so if you needed to find the probability of F and E, or the probability of E and F, but you have these two components, then you could do that. It's on your formula sheet. I actually don't think it needs to be on your formula sheet because you have this formula that does it all. Yeah. Is this the one that we did? Let me read it and confirm, but I think I'm able to copy and paste from the one that we did. It is the same one? Three children, find the conditional probability of having 2 boys and a girl, given that the family has at least 2 boys. Who has at least 2 boys?
No, I think we did like.
Yes, slightly different, but I can use the tree at least. I'm gonna cheat. It's gonna be kind of messy though. Yes. Copy. Paste. Okay. Now erase all the things that we are not using. I hate how it takes me out of the eraser when I lift it off. Oh, and this. There. probably took about as long as just drawing it out from scratch. So what this means is we want to find the probability of having two boys and a girl, given that the family has at least two boys. So you want to pay attention to that given, right? And in terms of our formula sheet, right, we have the formula for the probability of E given F. And so I always find that it's easiest if we define the first event as E, right? The one that we want to find the probability of. And then the second one, the given information, the family has at least two boys. Right, at least two boys. Let's call this F. At least two boys is two or three boys. So if we've defined our E and F, right, then we can find the probabilities that we need. Right? And so let's see here. Add a page. This down. So we want to find, let's map this out. Find the probability, maybe one more line. The probability of E given F. In general, is the probability of E and F divided by the probability of F. Remembering what E represents and what F represents, the probability of E and F would be two boys and a girl, which let's start off by circling those. Two boys and a girl, two boys and a girl, two boys and a girl. And they have at least two boys, which here they have three boys, here they have two boys, one boy, no, two boys, one boy, no boys. So now the overlap, the probability of E and F is going to be the ones where you've circled them twice, right? Which is those 3 out of 8 outcomes. And the probability of F, which is the blue ones, I'll do this. Just to show which ones you're counting. Right, the probability of F is 4 out of 8. You want to make sure that you use that total. And because they're both dividing by 8, we get an answer of 3/4. Do you mean this 4 or this 4? This one? So this 4 came from the probability of F, which is all the ones that have at least two boys, which at least two would be 2 or 3 boys. Which is this one, this one, this one, or this one, which is 4 out of 8. So that's where the 4 came. Nice. Good. For this question, I actually think it would be kind of hard to solve it without the formula. I don't really see it. I guess you could just map it out. Knowing that you're restricted to the blues, how many are orange? Okay, fine, you can just do it. Any questions about that one? On to the next one then. At a community college, 65% of students subscribe to Amazon Prime, 50% subscribe to Netflix, and 20% subscribe to both. If a student is chosen at random, find the following probabilities. What I want to list first, though, is what we've been given, right? Probabilities and percentages are interchangeable, right? And so if 65% of the students, then a randomly drawn student would have a probability of 0.65 of having an Amazon Prime account. Now, first, I'm going to let A be Amazon Prime and let N be Netflix. I kind of feel like maybe, but I want to use P for prime, but then P of P can sound confusing. So I'll do A, but I think a more natural choice would be P, as long as you can kind of keep those P's straight. You know what? No, live a little. Let's use a P. We can keep them straight. And for Netflix. That one's pretty self-explanatory. And we're given the probability of, P, Amazon Prime, is 0.65. The probability of N is 0.5. Usually I like to match 5-0. And the probability of P and N, which of course is the same as the probability of N and P, right? If you think about it that way, then it's really obvious that they're the same, but I'll write them down, is 0.20, right? They subscribe to both.
Would it have worked if I made it Venn diagram,
You totally could.
even though I like take away the 0.2 of the end, right? Because you have like the
So what you could do is you would have your universal set, your circles just now would be probabilities, right? And so you would have your P and your N, and then you'd have your probability of 0.20 in the center, which means that this area for Netflix would be 0.30, and for Prime, it would be 0.65 minus 0.2, putting me at 0.45. So you could do it that way. I guess it depends on what we need to find. The student subscribes to Amazon Prime, given that he subscribes to Netflix. There are lots of questions that you could solve this way. This one in particular doesn't lend itself to a Venn diagram with the conditional probabilities, but you can map out the probabilities like that. Yeah, I should have read what we need to solve for. We are in the conditional probability section, which makes it hard. So, well, let's see. Maybe we can get there. Might be hard though. We want to find the probability that the student subscribes to Amazon Prime given that he subscribes to Netflix. So what your first thing is mapping this out into notation, right? Focusing on this given. Which means you're going to write P given N. Arguably the hardest part, right, of kind of taking this problem and figuring out what you need to solve for. Because from here, the probability of P given N is the probability of P and N divided by the probability of N. Oops, I should use the and N divided by the probability. Probability of P and N is 0.2 divided by the probability of N. Now remember, the probability of N, the full probability of N is 0.5. You could get it from the Venn diagram, right? Knowing that they're in the Netflix circle puts you at 0.5 total. What's the probability that they're in the P circle as well? 0.2 over 0.5. But kind of tricky. Kind of tricky. Yeah. Nice 0.4. Again, the student subscribes to Netflix given that he subscribes to Amazon Prime. So pay attention to that given, right? And then map the question into notation from there. And so we want to find the probability of Netflix given Prime. Which is going to be the probability of N and P divided by the probability of P. The probability of N and P is the same as P and N, which is 0.2, and the probability of P is 0.65. 0.2 over 0.65, or roughly 0.3076923077. So quiet over there. Got me worried about time. It is, isn't it? Our very last section, new material, and then you'll have it all. I used to really enjoy, well, I didn't enjoy studying for final exams, but I really enjoyed the idea that nothing new is coming, right? And it kind of gave me an opportunity to kind of have an overview and say, okay, if I can just handle this, I'll be okay, right? And so it's always nice. It's our last section. So when we introduced conditional probabilities in the last section, I called them dependent probabilities. I said, okay, well, it might be helpful to think of them as dependent, right? A probability depends on what happened previously, right? And so now we're going to talk about independent events. Independent events would, of course, be, well, the probability of an outcome doesn't depend on anything. It just stays the same, right? And so if you flip a coin, for example, right, then the probability of heads is 0.5, right? Even if you know that you've flipped heads 14 times in a row, that does not affect the probability of the next head. It would still be 0.5, right? Which kind of leads us to the gambler's fallacy of, oh, well, I've flipped heads so many times in a row that it has to be tails now, but the probability actually stays the same, of course. Okay. And so let's see here. If you have a card, a card is drawn from a deck, and we want to find the following probabilities. I'll highlight that the given information. So here, the conditional or the additional information, the kind of given information may or may not alter the probability of an event. And so if it doesn't, then it's independent. So if we're drawing a card from a deck of cards, we want to find the following probabilities. Now, the probability of a king, there are 4 kings in a deck of 52 cards. And so the probability of a king is 4 in 52. And I promise no card problems on the final exam. You don't have to remember your cards. It's too hard. If we want to find the probability that the card is a king, given that the card is a face card. Let's see here. The probability of a king, given a face card. That means we have to remember how many, there are still 4 kings. And the kings are a face card, right? And so, but how many total face cards are there? There are 12, right? 3 of each suit. And so 4 over 12. Notice that 4 over 52 is different from 4 over 12. Right? And so it would depend on knowing that it was a face card. Hopefully, as opposed to here, I'll say these give different probabilities. Hey, now Claude is blabbing again. Still there.
Maybe they have to come around.
I'll be pulling that stunt on Wednesday. I think, if I can handle it. It's so boring for me. A card is drawn from a deck. Again, find the following probabilities. The card as a king is still 4 over 52, but let's just write it down. And then we want to find the probability that the card is a king given, all right, pay attention to that, given that a red card has shown. Right? And so we know that it's a red card, which puts me, now how I interpret this is we know, so one card is being drawn, and what we're told is that it is red. And then what's the probability that it's a king? Which is not obvious from how it's worded, in my opinion. Right? And so here, knowing the card is red, what is the probability? It is a king, is what we want to find. Oh, I thought it was a question. There are 26 red cards. Right? And then there are 2 red kings. So knowing that it's a red card restricts me to only having 2 kings, but it also is out of the total of 26 red cards. And if you use your calculator, right, 4 over 52, well, let's see if it does anything nice, is going to be the same as 2 over 26. You can subtract the 2 and make sure there's 0 if you want to make sure. All right. But notice that these are the same probabilities. Which means that the probability of a king doesn't depend on knowing if it's a red or a black card, right? It does depend on knowing, okay, if you know it's a face card, then that alters your probability. Right? But knowing the color doesn't. Maybe I'll crop this up to make it a little bit bigger. So independent events. 2 events, E and F, are independent if and only if, and we usually abbreviate if and only if in math to IFF, if and only if. At least one of the following 2 conditions is true. The probability of E given F is just the probability of E, or the probability of F given E is the probability of F. Notice the similarities here is it doesn't care about the given information, right? And so here, notice in both, the given information does not change the first probability. Of course, if the events are not independent, then they are dependent. And if one of these conditions are true, right, one of these 2, then both will be true, right? You might only have information on one of the sets, but they would be both true. On your formula sheet, oh, I guess I'm not. Well, kind of. We're kind of there. But we'll do this one first. Let me blow this up. So 2 events, E and F, are independent if and only if the probability of E and F is the probability of E times the probability of F. And so we usually only use this property to confirm whether E and F are independent. On your formula sheet, now we can bring it in. What you have, I'll do the very last bit of your formula sheet. Very exciting. We'll ignore this for just a smidge longer.
They go up to 15 bits of the definition.
There or more. Oops. We'll come back to this one. I really don't think that you need it. But the test for independence that we're talking about here is this one here. And where does it come from? Since the probability of E given F is the probability of E and F over the probability of F, that's from here, right? Just in general. And then if we solve for the probability of E and F, solve for the probability of E and F, what do? You have to get probability of E and F on its own. And how you can do that is you can multiply this probability of F over here, right? And so now you have the probability of E given F times the probability of F. Right, once I move it over here and then I revolving door it, which is what you have up here, right? The probability of E and F is the probability of E given F times the probability of F, or depending on what the given information is, right? The probability of F given E, but then you're multiplying by the probability of E, since that's the one that floated up top. And so here, I'll show that that came from there, and this came from here. Now, if E and F are independent, right, then we know that the probability of E given F doesn't care, so E doesn't care about F, and vice versa, F doesn't care about E, right? And so this, if E and F are independent, the probability of E given F is just the probability of E. Which is what we had up here, right? The probability of E given F is the probability of E because it doesn't care about F if they are independent, if and only if they're independent, right? And same thing here, the probability of F given E is just the probability of F because it doesn't care about E. It's independent of E, right? So piecing it all together, we get the probability of E and F is the probability of E times the probability of F if and only if, okay, that's important, E and F are independent. Which is why we call it the test for independence. Because we're not allowed to assume independence until we can prove it. Let's see here. Let me bump these down. We are not allowed to assume independence unless we're told that it's independent, but then you're allowed to, I guess. Unless, I guess, we are told it is independent. Or we have proven it using the test of independence, or we have proven it using the test for independence. Now, how you're going to use it is if you have all these components, you have the probability of E and F, and you have the probability of E, and you have the probability of F, right? What you're going to do is you're going to multiply the probability of E times the probability of F, and if you get the same answer, then they're independent, but they have to be exactly the same. So given the probability of E and F, the probability of E and the probability of F, we multiply the probability of E times the probability of F, and if the result is exactly the same as the probability of E and F, then they are independent. And if the result is exactly the same, has to be exactly the same as the probability of E and F, then they are independent. Then E and F are independent. See if I can. Oh yeah, sorry. More? Say one. Good.
What if we don't have the probability?
Then I can't ask you to do it. Are you good, Ken? Good. Thanks. Okay. I will have to give it to you. So I have to give you all three components in order to ask you if they're independent or not. For example, We have the distribution of colorblind people by gender. Right, we've got the colorblind versus not colorblind, and then we have males and females, and we have our totals, where M represents male, F female, C for colorblind, and N for not colorblind. And we want to find, are the events colorblind and male independent? And so what we want to do, and maybe I do need to put these on the next page here. Fine. Is the probability, so are the events colorblind, which is C, and male independent? So using the test for independence, right? If the probability of E and F is the probability of just E times the probability of F. So what that maps to is probability of C and F. Is it equal to the probability of C times the probability of, I used F, sorry guys. Couldn't keep it together. M. Probability of C and M, is it equal to the probability of C times the probability of M? Which of course means that I need to grab those probabilities, but besides that, not too bad. Now I'm going to work with the fractions because in order to be exactly equal, you can't have done any rounding, right? And so if you've done some rounding, then you'll want to be really, really careful. So I guess don't do that. Just use your calculator. What's the probability of colorblind and male? Colorblind and male is 6 out of 100. And notice how I put a little question mark over the equal sign because I'm seeing if they're equal, right? I'm not declaring that they're equal. The probability of colorblind is 7 out of 100. And so I get 7 out of 100. And then the probability of being male is 52 out of 100. Right, these probabilities are the overall probabilities. So 52 out of 100. So if you use your calculator and make sure you use your brackets, right? Let's try it and see what happens. 7 over 100 times 52 over 100. I get a nice 0.0364. And when I do 6 over 100, I get 0.06. Now these are clearly not equal to each other, which all that means is that C and M are not independent. Right? And it's kind of a well-established thing that males are more likely to be colorblind, and that makes it not independent. And so we say, therefore, the events C and M are not independent. So that's how you would show whether two things are independent or not. And check the. Okay. Pick up the pace a little bit because we can do it. We can finish it. In a city with 2 airports, 100 flights were surveyed and 20 of those flights departed late. 45 of those 100 flights in the survey departed from airport A, and 9 of those flights departed late. This 9 is out of the 45, right? And then 55 flights in the survey departed from airport B. So 11 flights of those 55 departed late. Of course, 45 and 55 makes 100, and 9 and 11 makes 20, right? And so here we've got our broader information, and then here we've got our airport specific information. Now, what we want to know is, are the events depart from airport A and departed late independent? So we can let this be A. Let A denote the depart from airport A, and we can let departed late be denoted by an L. And we want to show if the probability of A and L, is it equal to the probability of A times the probability of L? This one's a lot trickier than the table, in my opinion, right, for finding these probabilities. The probability of A and L, they have to depart from airport A and they have to be late. And so 9 out of 100 of those flights were A and L. The probability of A is a little bit easier, right? 45 out of the 100 flights departed from airport A. And in general, 20 out of 100 flights were late. Making sure you use some brackets here. Yeah, sorry.
Why would the probability of airport A and late not be 9 out of 45? Because you have 45 flights in airport A and 9 out of the 45 are late.
So that would be the conditional probability. The probability of late given that they were departing from airport A. And that's the tricky part. But if you just want all of them, then it has to be out of the total 100. Yeah. So using your brackets, 45 over 100 bracket times bracket 20 over 100 and bracket, I get 0.09, which looks promising. 9 out of 100 is also 0.09. Now, because they're exactly the same, then we can say that departing from airport A and departing late are independent events. Therefore, the events A and L are independent events. if a coin is tossed 3 times and the events E, F, and G are, E is that the coin shows a head on the first toss, F is at least 2 heads appear, and G is heads appear in 2 successive tosses, right? A couple of ways that we could have that happen. And we want to determine whether the following events are independent. Oh, this feels long. How much time do we have? Can I be sneaky and put this one off until the end so we can actually maybe finish it? And then if we don't have time to finish it, I'll put it in the notes before I post it. You can try it. How about that? Uh-oh. Now I've done it. Because we're this close to finishing it all. And I don't want to waste our breath. And this one's going to fit here. The probability that Jamie will visit his aunt in Baltimore this year is 0.3, and the probability that he'll go river rafting on the Colorado River is 0.5. Wow, must be nice to be Jamie. If the 2 events are independent, what is the probability that Jamie will do both? And so this is one of those scenarios where we are told they are independent. And so what does that mean? This tells me that I'm allowed to assume that the probability of E and F is the probability of E times the probability of F. And I'm allowed to use that property. And lucky for us, that is the probability that we want to find. What's the probability that Jamie will do both? And so let's see here. The probability of going to Baltimore is 0.30. Okay, bless you. And the probability, bless you, of river rafting, let's call it R, is 0.50 on the Colorado River. And we want to find the probability that Jamie will do both, the probability of B and R. From our general formula, the probability of B and R is the probability of B times the probability of R. Bless you. I've been sneezing nonstop today.
This room
I
and I are not friends.
Oh yeah, this room, yeah. But for me, it's been all day. But I'm not sick. It was just, it felt like allergies, which is weird.
I know, this is the
Kinda
only
weird.
room I sneeze in. I swear I don't sneeze anywhere else on campus.
Yeah. I can see dust bunnies, so
Yeah.
but knowing that they're independent, I'm allowed to multiply them to get 0.3 times 0.5, and I get the probability that he'll do both is 0.15. Because true to form, I feel like they do a hard example and then a bunch of easy ones. If we know that the probability of B given A is 0.4, if A and B are independent, find the probability of B. Right? If they are independent, what does that mean? If A and B are independent, then the probability of A and B is the probability of A times the probability of B. Oh, sorry, I missed it. It's a sneaky one. We want to find the probability of B But the probability of B, if A and B are independent, is the probability of B given A. So I shouldn't have done this. It's still true, but I'll put it here. Since A and B are independent, the probability of B given A, well, the probability of B doesn't care about A, so it is just the probability of B. Therefore, the probability of B is 0.40. Sorry, I tripped you up with the general formula there. Still true, but we didn't use it. If we're given the probability of A is 0.7 and the probability of B given A is 0.5, and we want to find the probability of A and B. Now, if I have this probability, this conditional probability, there's no mention of them being independent, and so I'm not allowed to assume that. Which means I'm back to where we were, right? Probability of B given A would look like this. Is the probability of B and A over the probability of A. The probability of B and A is the probability of A and B. And so what I'm looking for is that numerator. Right? Now I have the left-hand side, the probability of B given A is 0.5, is the probability of, and I'll swap it just so it looks the same, right? But just remember that it is the same thing, A and B. All right, and I'll just kind of take it down here. Divided by the probability of A, which is 0.70. Solving for the probability of A and B. I get 0.5 times 0.7, which is 0.35. Just
I don't care that we go over, but I know there's another.
oh my gosh. Thank you. Luckily, we've already talked about these. If they're not independent, then you can rearrange and solve for the probability of E and F. Either way, it's on your formula sheet. I'll do these last two examples. We almost made it before I post the notes, so you can try them on your own. End of new material. We'll do some practice on Wednesday. If you have any questions, let me know. Otherwise, see you Wednesday. And thank you. It's over.